approximate integration. Instead of finding the exact area under the curve, we're going to find some approximations using midpoint rule, trapezoid rule, talk briefly about Simpsons, which is not really a key topic, and take a look at what this type of questioning might look like when we get to the AP exam. Now, midpoint rule is something that we've done before. We have made rectangles and we've estimated the area under the curve using Riemann sums using midpoints. So what we're going to have to do is just take the change in x and multiply it by the height of the first rectangle, which is found at the midpoint, height of the second rectangle found at the midpoint, and on and on and on, like we've done in the past. So if we're going to find the area under this curve right here, I have found values of 1 over x squared between 1 and 2, and I put them in this table, only accurate to 2 decimal places. But just to get a feel for the midpoint rule, if we're going to make 5 rectangles, and we're going to start at 1, we're going to end up at 2, then each jump is going to have to be a jump of 0.2. Remember, when you're doing midpoints, you got to make sure when you're finding the area using midpoints that the numbers actually do appear in the table. We're forced in this problem to make jumps of 0.2 so that we do have the actual midpoint in the table and a value for the function at that midpoint. So we'll take 0.2 as our change in x, and our height at the first midpoint is 0.83. Our height at the second midpoint, the midpoint of the second rectangle, 0.59. The third rectangle, 0.44. Fourth rectangle, 0.35. And the fifth rectangle is 0.28. So this was nice and convenient because in this table, all of the jumps are the exact same size. So we can just put that change in x, that constant change in x out front. Oftentimes in tables on the AP exam, we're going to have to find the areas of rectangles very specifically because they don't all have the same change in x. If we multiply this out correctly, I think we get 0.498 as the area under the curve. So that would be midpoints, and we've got some experience doing that. Now we're going to move to trapezoids. And remember how to find the area of a trapezoid. If I have a trapezoid that looks like this, and this is base 1, which is parallel to base 2, and this is the distance between those parallel sides. That's known as the height, even though in these types of trapezoids that runs horizontally, still considered the height. It's the distance between the parallel sides. The area of a trapezoid is 1/2 times the height times the sum of those two bases. Now, if we were to put another trapezoid right next to that, and again, we're going to keep this thing to be a constant value. We're going to call that h. We're going to again have 1/2 the height and the sum of the bases. Well, these two trapezoids share this side, so this is going to be base 2 plus, and this one, maybe I'd call this base 3. And the reason that I point this out is to realize that base 2 gets used a couple of times. So if I'm using the same table of values, and I want to make a total of 5 trapezoids, the trapezoid rule says take your change in x, divide it by 2, because the change in x is what amounts to be in this height right here. So the change in x divided by 2, and then multiply that by, well, we used this guy one time. So that's f of x sub 0. Everything between the beginning and the end, everything in between, like this B2, is going to get used twice. It's going to appear in a couple of different trapezoids. If I were to continue drawing here, this B3 would be used in the red and the green trapezoid. So that's why we see 2's in front of all of these heights that occur in between. And when we finally get to the end, let's say this is the end of our region here, well, that guy, B sub n, or the end of the interval, that guy only gets used one time. So it's one of the heights at the beginning, 2 of everything in between, and then only 1 at the end. So if we use our trapezoid rule, we're going to find 5 trapezoids, and again, we're going to be jumping like this. We'll take our change in x, and our change in x is 0.2. And since we're finding areas of trapezoids, we've got to take that height and divide by 2. All right, now we've got to take these bases. Well, the first base is 1. We only have 1 of those. We've got 2 of these 0.69s. We've got 2 of these 0.51s. We got 2 of these 0.39s. This 0.31 is going to appear in 2 different trapezoids. But the end, when x is 2, this rate of 0.25 occurs only in that final trapezoid. And if we multiply all this out correctly, I believe we get something like 0.505. Trapezoids are really pretty accurate. You think of a curve like this, and we start making trapezoids. Let me make those in red. We start making trapezoids, you don't have as much waste as you do with rectangles. Seems to hug the curve pretty nicely. So trapezoids are a nice, accurate way to get an approximation for the area under the curve rather than an actual area under the curve. Then there's something called Simpsons, and I've talked about this more in the past, and I'm not going to talk about it as much today. It's just not an AP topic. It is a very accurate way of finding the area under the curve, because what it does is, instead of rectangles, instead of trapezoids, what it does is somehow it puts little pieces of parabolas at the top of each one of these regions. You can see that those are going to hug that probably even better than those straight lines like the trapezoid does, and certainly less wasted space than when we use rectangles. So that's Simpson, but anytime you see Simpson as part of the assignment, I think I've changed those to trapezoid rule. So we really aren't going to worry about Simpson here. All right, so you've got the areas one program in your calculator. And you're going to find the area under this curve from 0 to 1. And you are going to make 6 trapezoids using that action, 6 midpoints, And just for giggles, why don't you go ahead and make 6 Simpson regions. And if you want to press pause now, do that on your calculator. Come back and we'll talk about what those actual answers should be. So if you did this correctly on the calculator, this is 0.257-ish, I believe. And we said trapezoid's pretty darn accurate. Midpoint's also pretty darn accurate, 0.246. And Simpson regions, you get 0.25. Now, if we had used the fundamental theorem of calculus, we would have found the antiderivative. If we evaluate this integral between 0 and 1, we're going to put 1 in there, 1/4 minus, and you can see that Simpson really gets this accurately. And the problem with Simpson is that it's not something that we have experience with in the past. They have recognizable shapes like a trapezoid or like a rectangle. And so therefore, AP doesn't use Simpson regions. I have 2 more examples, things you might see, typical kinds of things you would see on an AP exam. Finding this area under the curve using a trapezoid rule. Let's make 3 trapezoids. We've got a change in x. We're going to use one of these guys. We're going to use 2 of those guys. We're going to use 2 of those guys. And we will use 1 of those guys. And I'll let you guys put that in your calculator to figure out what that is. A trapezoid rule using a table. Now, this is more accurate as to what you would actually see in the AP exam. Called a trapezoidal sum. 4 intervals. 1, 2, 3, 4. And you'll notice that these changes in x are not consistent. And that's what you should expect to see in the AP exam. We got to find the areas of 4 individual trapezoids. So we got to take a change in x divided by 2, height 1 plus height 2. Our second trapezoid, change in x is 6. 1 plus height 2. Third trapezoid, change in x. Missed that one. Change in x again is 8. Height 1 plus height 2. Or base 1 plus base 2. And finally, final change in x. Divided by 2. Base 1 plus base 2. And even when we do it this way, we see that these in between the beginning and end, each one of those bases gets used twice. Calculator time. If you do this correctly, I believe you get 115. So that's how we're going to use midpoints and trapezoids to estimate the areas under the curve.